On an autumn evening in 1989, Tom McMahon noticed some unusual construction getting started in his Los Angeles neighborhood. As more and more trucks began showing up with bizarre power tools, test equipment, and tanks of liquid nitrogen, his curiosity got the better of him and he had to take a look. He learned that a high-voltage underground transmission line had experienced a fault, costing the city tens of thousands of dollars per hour in lost capacity and downtime. Over the next few months, he got more acquainted with the project manager for the repair, and he shared all the fascinating details of what he learned in a series of messages on his company's mailing list. Those messages spread like wildfire across various bulletin boards, lists, and forums of the early internet. I don't remember exactly how old I was when I came across this story, but I do know it was one of the very first times I realized how awesome infrastructure and engineering could be. I figure if it had such a big impact on me, that it's a story worth retelling, especially because there's a recent update at the end. Maybe it will inspire others to be more interested and engaged in their constructed environments like it did for me, which is basically my entire goal with these videos. I'm Grady, and this is Practical Engineering. In today's episode, we're discussing the Scattergood Olympic underground transmission line. How do you get electricity from where it's generated to where it's used? That's the job of high-voltage transmission lines. Electrical power is related to the product of voltage and current in a transmission line. If you increase the voltage of electricity, you need less current to deliver the same amount of power. So that's exactly what we do. Transformers at power plants boost the voltage before sending electricity on its way, usually in 3 separate lines called phases, reducing the current and thus minimizing energy wasted from the resistance of conductors. High voltages make electrical transmission more efficient, but they create a new set of challenges. High voltage electricity is not only extremely dangerous, but it also tends to arc through the air, which is not a great insulator, to the other phases or grounded objects. The conventional solution is to string these lines overhead on towers. This keeps them high enough to avoid contact with trees and human activities, but the towers serve a second purpose. They keep enough distance between each line so that electrical arcs can't form between them. Unfortunately, stringing high voltage lines overhead isn't always feasible or popular with the local residents, especially in dense urban areas. That was true in the 1970s when engineers in LA were deciding how to expand their transmission system and deliver power from the Scattergood power plant to the Olympic substation near Santa Monica. So they tried something that was relatively new and innovative for the time. They ran the line underground. 3 230 kilovolt lines, one for each phase, would deliver enormous amounts of electricity over the approximately 10-mile or 16-kilometer distance in West Los Angeles, powering hundreds of thousands of homes and businesses. However, putting high-voltage lines below the ground created a whole new set of challenges. When strung across towers, the conductors at this voltage each require around 10 feet or 3 meters of clearance to avoid arcs. The air is the insulator, doing the job of keeping electricity constrained within the conductors. So how do you take those 3 high voltage phases and cram them into a single small pipe running underground? Well, you need a better insulator than just air. One of the more popular options of the time was to use high pressure, fluid filled cables. This design starts with installation of a steel pipe below the ground with access vaults spaced along the way. Copper conductors are surrounded with many layers of paper insulation. Next, a protective layer of wire, called skid wire, is spiraled around each one to protect the paper from damage and allow for easy sliding along the pipe during installation. The conductors are pulled through the steel pipe using massive winches and then spliced together at each vault. Once the steel pipe is fully welded closed, it's slowly filled with a non-conductive oil known as liquid dielectric. This oil impregnates the paper insulation around each conductor to create a highly insulative layer that prevents arcs from forming even with the conductors sitting mere inches apart from one another and the surrounding steel pipe. At the same time, the oil works as a heatsink to carry away heat generated from losses in the conductors. It is critical that the oil completely saturates the paper insulation and fills every nook and cranny within the pipe. Just like a hole in the plastic insulation around an extension cord, Even a tiny bubble in the oil can create a place for arcs to form because of the extreme voltages. So the oil inside the pipe is pressurized, usually around 14 times normal atmospheric pressure or over 200 psi, to ensure that no bubbles can form. The rating of a transmission line, in other words, how much power it can deliver, is almost entirely based on temperature. All conductors, with rare exceptions, have some resistance to the flow of electric current, and that creates heat, which will eventually damage the conductors and insulation if it builds up. The more heat you can remove, the more power you can push through the line. That's a major benefit of pipe-type oil-filled cables. They're surrounded by a gigantic liquid heat sink that can be circulated to keep the temperature down and prevent hot spots from forming in the lines. At each end of the transmission line is a plant filled with pumps and tanks to pressurize and often to circulate the dielectric oil in the pipe. This particular transmission line in LA circulated the oil in 6-hour cycles. At the end of each cycle, the pumps reverse to move the fluid in the opposite direction through the pipe. Some systems are different, but for the scattergood line, this pumping is a slow process. You're not trying to pump all the fluid from one end of the line to the other, but rather simply get it to move a short distance along the line to average out the temperatures and minimize the possibility of any single section from overheating. However, even at that slow speed, you can't just switch the flow direction in an instant. I have a video all about a phenomenon called fluid hammer, and you can check that out if you want to learn more after this, but I'll summarize here. Moving fluid has momentum, and rapidly changing its velocity can create dangerous spikes in pressure. Water hammer can be a problem in residential homes when taps or valves within washing machines close too quickly. You might hear a pipe knocking against a wall, or in worse cases, you might completely rupture a line. However, in large pipelines that can contain enormous volumes of fluid, reversing a pump can be the equivalent of slamming a freight train into a brick wall. To avoid spikes in pressure, which could damage equipment or rupture the pipe, the pumps at either end of the scattergood Olympic line would spend the last hour in the 6-hour cycle slowing the oil down, providing a smooth transition to flow in the opposite direction for the next cycle. Circulating the dielectric oil helps to keep the temperature within the pipe consistent along the line, but it can't control how that average temperature changes over time. Transmission lines don't deliver a constant current, rather the current depends on instantaneous electricity demand, which changes on a minute-by-minute basis depending on the devices and equipment being turned on or off. When demands fluctuate, the current in a transmission line changes, and so the amount of heat in the line increases or decreases accordingly. As you might know, many materials expand or contract with changes in temperature, and that's true for the copper conductors used in underground transmission lines. When these lines expand within the outer pipe, they often move and flex in a process called thermal mechanical bending, or TMB. If not carefully designed, these bends can become tighter than the minimum bending radius of the cable, exceeding the allowable stresses within the material. Over hundreds or thousands of cycles of TMB, the paper insulation around each conductor can begin to soften or tear, eventually leading to a dielectric breakdown. In other words, arcs and short circuits. TMD can also pull large diameter splices into narrower sections of the pipe, causing them to rub and abrade. That's what happened in 1989 to the scattergood Olympic line. But before the LA Department of Water and Power could repair the fault, first they had to find it. Locating a fault in an underground line is half art, half science, and there are many interesting types of equipment that can be used. They tried to use ground-penetrating radar along the line, but they couldn't identify the fault. They also tried time-domain reflectometry, a method of transmitting a waveform through the cable and measuring the reflections, but the results weren't conclusive. They also used a device called a thumper, which introduces impulses of high voltage into the cable. When this impulse reaches the fault, it causes an electrical arc which can be heard as a thump above the ground, usually aided by a handheld detector with a microphone and digital filters. Going from one extreme in technology to the opposite, the crews used car batteries and voltmeters to take measurements of the conductor's resistance between tap points to precisely identify the location of the fault within Mr. McMahon's neighborhood. Once found, the challenge of repairing the faulted cable could begin. How do you fix an insulated conductor inside a steel pipe bathed in high-pressure oil? With liquid nitrogen, of course. Pumping all the oil out of the pipe before the repair wasn't feasible. It couldn't be stored and reused after the project because that process would introduce contaminants that would reduce the oil's insulative properties. They also couldn't dispose of it and replace it with new oil because the stuff's expensive and it would take a long time to get in such incredible quantity, potentially extending the very expensive downtime. Even more importantly, relieving the oil pressure from the rest of the pipe could allow gas bubbles to form inside the layers of paper insulation, potentially damaging them and creating new places for faults to form. The clever solution they used was to freeze the oil using liquid nitrogen, which is usually around -200°C or -320°F, creating solid plugs on either end of the section to be repaired. This allowed the rest of the pipe to remain under pressure. Losing these plugs would be a catastrophe, creating an eruption of high-pressure oil and spilling huge quantities of it into the environment. So the repair crew had liquid nitrogen companies on call across California as contingency to ensure that the oil could be kept frozen for the duration of the fix. Unfortunately, after taking X-rays along the entire length of the line, they realized that many of the cable splices were in danger of experiencing a similar fault due to thermomechanical bending. After coming to the conclusion that this wasn't going to be a quick fix, the Department of Water and Power decided to drain the entire line of oil and implement preventative measures while it was already down for repairs. Aluminum collars were installed at key locations along the pipe to constrain the thermal movement of the cable. This was done in a semi-clean environment with air handling and cleanliness requirements to prevent contaminants from finding their way into the pipe. After many months and tens of millions of dollars worth of downtime, the trucks and crews finally pulled out of Tom's neighborhood, and the underground transmission line was finally brought back online. There's an update to Tom's story that brings us to modern times. The Scattergood Olympic line's troubles didn't end with the work in 1989. LA's routine testing showed that the insulation was continuing to degrade, and outages on the line were significantly disrupting the reliability of their transmission network across the city. In 2008, the Department of Water and Power began developing a replacement project, this time using newer cable insulated with polyethylene instead of high-pressure oil. After 10 years of planning, environmental permits, public meetings, design, and construction, the project was completed in 2018. The original transmission line is still in place and can be used as a backup if it's ever needed. As a part of my research for this story, I spoke to Tom on the phone. He told me that shortly after his write-up spread across the early internet, it was sent to a teletype machine within one of the offices of the LA Department of Water and Power, providing some higher up within the organization a neatly printed version that may or may not be still hanging on a wall somewhere downtown. Huge thanks to Tom for taking the time all those years ago to share his enthusiasm for large-scale infrastructure. Thanks to Jamie Zawinski for preserving the story on his blog. And thank you for watching. Let me know what you think.